Previously we talked about DAC, right? Now we talk about ADC, analog to digital. Okay, so you have to comparatively ADC, okay, requires a referencing voltage in order to run ADC. In DAC you don't need a reference voltage. Okay, I think you may need lah. Yeah. But nonetheless, let's go on. Okay, I think DAC don't have lah. No need referencing. Okay, because wherever thing from the digital side, okay, you all the voltages will all comes in, and then will translate analog. Analog meaning you're talking about mechanical systems. Okay, so digital side you have some voltage and then you all put it in and then you reference. So whatever voltage you output the whatever voltage from whatever inputs that you have. It's quite straightforward for DAC. For ADC, you need a referencing one, so you need a comparator. So this is the op amp. If you remember, we're talking about the op amp. So the op amp itself can be used as a comparator also. So comparator itself is a V in this side. So V in this side means that there is an inverting. So we are still talking about the inverting amplifier now still. Okay. So inverting side, um, okay, these are the things first. So this is used for a ADC system. Okay, and then more clearer view lah. Okay, so you know that this op amp can be can be a comparator, right? So you compare between the V in, as you can see if you follow this thing. Okay, you are going into here, into this point, into this node over here. So maybe I should hold on. So you have a V in over here. The V in will comes in, and it will at this node it will goes in. So if it compares to your V reference, so there will be another voltage over here to reference. Maybe I should have another color, so there will be like this color over here. So you're comparing this one and this one. So is this green color larger than red? If it's not, okay, then the red color will go, and then you turn it off lah. Okay. So this one will go through here and such. Okay, while the V reference, this is V reference, right? So this is the red color is the V in. Okay, whatever voltage you input. V reference is controlled by the number of resistors. Okay, it's like a binary also. So it's like two at this point the voltage is the highest, right? It's the highest. So certainly the voltage here should be the resistance should be highest also, because V equals to IR, assuming that I is the constant. So in this case this is 8R, so it's like a 2 to 3, and then this is 2, this is 7R, 6R, 4R, 5R. So it's like a beat type of thing, but in this case I don't know how to represent the resistance, but whatever. So this is how it works. So you're comparing the in and the reference. And the first thing I need you to understand is that this is the very important keynote, okay, A and B at this point. This is called the XOR, the exclusive OR gates. So if it's 0 0, you have output 0. If it's either one of it, you have 1 output. Okay, so what does this mean? So if my V in is, let's say, 5 volts, and then my V reference, maybe this is like 8 volts, 7 volts, 6 volts, 5 volts, 4 volts, 3 volts, right? So if my V reference, let's say my V in is 5 volts, you reference your 5 volt. Okay, yeah, this is your 5 volts compared to 8 volts. If this in this case your is lesser, right? Because the V in is lesser than the V reference, so this will become 0. Okay, so when it comes here, it is 0. This is 0, so you will not have anything at all. Okay, so this applies to the same as the 8765 up till 5 lah. Okay, up till 5. As you can see, if you were to go to 5, this will be a 5 volts. Okay, and your V reference At this point, it goes into here, 5 volts. So since they are the same, you open up, allowing this to be 1, right? Allowing this to be 1. But as you know, because this 6 volt is actually the referencing voltage, right? So this 6 volt is still larger than the 5 volt over here if you were to do this. This is 5 volt, this is 6 volt. So in this case, this will output 0. This will output 0 over here, right? So this will output 0, this will output 0, 0, 0. So these are all, so this portion over here are all 0. Because 0, 0, you get output 0, right? I mean, yeah. So up to here you have 0 and 1, okay? 0 and 1. So you can output you have a 1 over here. So later on you will know what are the encoder things that happens. But nonetheless, this is the very important understanding, the 0, 0, 0 and 0, 1. Either one of the A or B lights up, you have output of 1. Okay, if it's 1, 1, then you have an output of 0. So this is a very key understanding you must first know. Okay, remember this, you must first know. First know. Download inside your brain. Okay. So in this case, yeah. And as you can see, if this in the case this is 5, because this is also 1, right? Yeah. In this case, this is 5 volt. This is 4 volts, right? So maybe I should bring the green color over here. This is 4 volts. Compare, this is actually 1, 1, right? So 1 and 1, if you take a look in the graph itself, table itself, 1 and 1 you have an output of 0. So this is why you have a 0, and the rest should be also zeros, right? So this is why this is the smart method of doing these things. Although it's very tedious for us. Yeah. So so in the next page 11, okay, you have a something. Okay, so this is actually the same thing as a tutorial 1, question 11, I think. Yeah, so we are talking about the last question of the tutorial already. Okay, so the later on I'll talk about it in more details. But what I want to convey in this is to actually compare different ADC approaches. So in this case, this is actually called the flash ADC, simple and powerful. Okay, it requires one comparison, but it's very intensive because you need a lot of planning and such. Okay, and you need a lot of diodes and things like that. So it's very you need, yeah. So the analog input is the green color curve, right? So your digital output is this red color line. You can see it is quite nice. It's a RAM output actually. So it's quite okay, not bad. That's what it is lah. And then if you do, so this is the flash ADC. Okay, so maybe I should put it in. Yeah, so this is flash ADC. Second one is actually digital RAM ADC. This is something different. So what does this do is actually the SRG takes in the input. Okay, it takes in the input. I don't know where the fuck is input. I think here. Yeah. So from here it takes in the input, and then the input also goes through the CTR. So the CTR generates a steadily increasing binary number. So you generate a number based on using some of the concepts of this. Okay, and then you blah blah blah, and then you're comparing this one and this one together. So this shift register outputs the correct value once reached, then resets the counter. So it compares the input, okay, with its inner thing lah, okay, inner referencing voltage, and then you output whatever things. Okay, so this will be the binary output over here. As you can see, this is the lines binary output. Okay, so this is the binary output, and this is where after when you output already, you restart everything again, refresh again, and then you have a new voltage comes in, and then you feed, and then you have another voltage. Then you have the beats, everything, and then you connect to the SRG, and then you compare again. So what the hell is DAC? DAC is actually to convert the counter output to a voltage. Okay, is to convert the counter output. This is the counter. So the counter output goes to DAC, and then you have a certain voltage, and then you feed back to the inverting side. Okay, so this DAC is actually acting as a feedback system, so then you can actually compare with the V in. Okay, so in this case, this is the V in. So this is actually what? This is actually called the non-inverting amplifier. Okay, so you're actually referencing between the input and the output. So this is the thing for what we call digital RAM ADC. So this is less component intensive, meaning it is it is less it's lousier than this one, okay. But then yeah, and then nonetheless the output is also lousier. You can see this is your input, then your output is slightly off and then you also take a longer time also, you see. You take a longer time, you take a shorter time. So there is a time issues over here, slow different conversion time. So this is the thing you need to know for digital RAM ADC. The other successive approximation ADC is a little different from RAM. Okay, the only difference is SAR. It's only this one. SAR, this one is CTR. The rest DAC and SRG is the same. Okay, they act for this case, for successive one, these two are the same. They do the same job lah. Okay, primary. But however, SAR they do the different job. For this case, your output is connected into the SAR. Okay, and then you compare with your grid. Where's your input? Good job. You connect your output same as your digital RAM. You connect your output over here, and then you compare with your input, and then you get whatever things. So this one you put in your output, and then you compare with your input also. However, you have a output sent to the SRG to compare with the output from your SAR from this side also. So you have two type of outputs from your SAR. So in order to make things like more accurate lah. But however, it's still not that accurate compared to the flash ADC. But it should be more accurate than digital RAM. Okay, so this is the things that you need to think about. Okay, and then so the next one is tracking ADC. Okay, it's totally different from the digital RAM and successive. It's you have a counter UD. Okay, up down counter, meaning I think up down means the binary one, so it's like 1 or 0, 1 or 0. So you have to count it like like manually type of thing. So you're gonna calculate it in this manner, and then you output to DAC, and this DAC will DAC will output back to the input, and then nonetheless this CTR output will actually output to the binary. I mean will output to this thing will straight away output lah. Okay, don't have any filter like SRG. SRG is actually adds to compare with the output in order to ensure that the output and the previous output and the new input. Okay, this is the new input. Okay, let's say digital RAM ADC lah. This is the new input comparing with the previous output, and then you compare whether are they the same, and then you output. But however, for tracking ADC, you don't have any comparison. Your previous output is straight away sent to the counter, and then you straight away compare with you do whatever things okay, I don't know what the things are, and then you straight output. But what are the key things you need to take note is, as you can see, it's a very small steps. Okay, very small steps. So it's very meticulous. Okay, it's trying to meticulously follow the input, and then you try to create an output that is almost about the same trend. Okay, but however it takes a lot of time. As you can see, it's meticulous, but yeah, time. So the time itself is very tedious, but your signal is very good. But if it's a very large output, okay, if it's a very large output, so if you want it fast lah, then you need to count bit by bit, which is this one lah, and then which may be a little off the graph. But if you want a slow slow timing and a good signal, while low cost, right, use tracking ADC. Low cost, slower time but good signal, tracking ADC. And then for successive approximation, slightly compromised signal, okay, with a slightly compromised time. Okay, you need a lot. You need like faster time than this one. Okay, although it's faster, but then signal is also lousier. So so if you want to rank, right, rank, this one is the best. Okay, maybe hold on a while. I draw up the table lah.